It even tells you go! Exclamation point. Yeah. Okay, so organometallics, we're only doing Gillman reagents and Grignard reagents out of this chapter. So there's a whole bunch of content about how to swap metals using more electronegative metals, and then there's the Suzuki reaction and these other palladium-based reactions like the heck. And we're not doing that. We're just focusing on the Grignard and the Gillman, because those are the classics, and they're incredibly useful tools. And the other ones, like I said before, every book adds a couple extra things to make their book unique, but I don't think that those reactions are things we need to build on or necessarily use. So we've typically been seeing carbons behave as electrophiles. Where a nucleophile can come in and attack the carbon as an electrophile, kicking off a leaving group. Because of that partial negative character, partial positive character on the carbon. Now, what we're going to look at here with organometallics are ways that we can make this carbon the nucleophile. So to do this, to make a carbon act as the nucleophile, you need to bind something to the carbon which pushes the electrons towards the carbon. So in other words, something that's less electronegative. So we do that by putting a metal on the carbon. And metals are fantastic at losing electrons and stabilizing positive charge, meaning they are not very electrophilic. So what this does is it actually keeps the electrons on this carbon more than on the metal. And this lets this carbon act as a nucleophile. So what this looks like is if we have this react with some electrophile. We can do this. Now, the cool thing about this, and I talked about this very briefly, is we don't have that many reactions that let us form new carbon-carbon bonds. And one of the reasons was, and we had that one with the terminal alkyne, because we had the negative charge on the carbon, which allowed it to act as a nucleophile. Well, the same thing applies here. Now that we have this nucleophilic carbon, you can now do nucleophilic attacks with this kind of carbon on this kind of carbon. And you can get new carbon-carbon reactions. So you can do these Grignards on a host of different electrophilic carbons. Now, let's see.
What is the Z?
Just some placeholder for the leaving group.
Leaving group.
Yeah.
Is the metal neutral after the reaction? Or
No, it's going to get the electron. It depends. It depends on what the organometallic is. So when we get into it, we'll sort out what's going on with that metal specifically. It likes to be positive, but it depends. So the first one that we're going to do, and we're not going to practice using this one as much because we're going to use it a lot next semester, is the Grignard reagent. I know when people miss class when they come to office hours after missing class, which is because it's the Grignard. Yes, the Grignard. Everyone wants to know about the Grignard reaction when they don't come to class. So it's like somebody waving the white flag. I didn't come, and I'm admitting to it. So Grignard reaction is probably the most commonly used. We do it in organic chemistry lab. It's a fantastic, robust reaction. And it works on alkyl halides. It works on vinyl halides. It works on aryl halides. So, and it does proceed through an SN2 mechanism. So that's what really limits the Grignard, is it is an SN2, so you have to work within the constraints of an SN2 reaction. And it's, let's see here. Well, I'm jumping ahead of organolithiums, but we can do that. So what we do is you combine an alkyl halide, in this case, plus metallic magnesium, finely shaped magnesium flakes, and then you use diethyl ether or THF as a solvent. Either of the two work. Diethyl ether is the one I've used nearly exclusively for this reaction, because it does a really good job of complexing and solubilizing the magnesium as it's binding. And what this does is, let's see here. Let me actually put one together here. So let's say we've got our alkyl halide, and we react this with magnesium in diethyl ether. That's what you get as a product, which is your Grannard reagent. And what this does is this functionally reacts with this carbon behaving. This is not what it truly is, but this is analogous to this reacting as a nucleophile. It acts like a carbanion in terms of how you would predict a product. So there's this really nice partial negative charge on this carbon, partial positive charge here. Disconnect as a nucleophile, do an attack, this falls off, and you get a nucleophilic attack. And most of the time, we're going to be doing it on other carbons. Let's see. So this is a Grignard, and there's another variation of this style of reaction using lithium, which is slightly different. It's not technically a Grignard, and I haven't done this one before, but it leads into the Gillman. So let's take a look at using lithium as a metal here. So for organolithium, what you need is hexane, a really good nonpolar solvent. And let's see here, let's just do, you need 2 equivalents of the lithium in this reaction to set it up. So for every alkyl halide, you need a pair of lithium. You run this in hexanes, and what you get CH2 is just the lithium plus the lithium bromide, which is why you need that second equivalent of lithium. So in this case, it just binds the lithium. In the Grignard, you get a magnesium plus your equivalent here, but this is supported separately from the lithium. So this is just the same kind of effect where, whoa, it's going the other way, where we get our partial negative charge on the carbon, our partial positive charge on the lithium, and this lets this carbon act as a nucleophile. And that's going to let us set up a Gillman reagent once you have your organolithium compound. So a couple quick important things to review. These are very strong bases. So how strong is a very strong base? Stronger than a hydroxide. Strong enough to pull water apart to grab the proton and form hydroxide as a product. So this is such a strong base that if you have water, it will pull the water apart to make the conjugate acid plus hydroxide, because hydroxide is a more stable base, less reactive base than this is. So, excuse me. Because of this, you have to have solvents that are acidic proton free. You can't use water, you can't use alcohols, you can't have water or alcohol contaminations in your solvents. If you have wet diethyl ether, your Grignard reaction will not work, because as it forms, it will react with a trace water in your solvent, and what you'll get is, let's say we've got this, and you react it with magnesium and THF. And you get your Grignard reagent, but there's water hanging out. This will behave as a hydride, attacking the proton, kicking off a hydroxide, and you will end up with that as your product, not as a Grignard, because the Grignard will subsequently just react with water and pull that proton off, and then you no longer have a Grignard. So you're not going to be able to get, this happens in OChem lab a lot, because in the Grignard, the magnesium comes in and then complexes to the bromine also, and it's the organolithium compound that's only the lithium, and then the lithium bromide or lithium halide falls off to the side, which is why you need two equivalents in the lithium. Yeah?
Can't in alkyl halides, the hydrogens from the carbon have some sort of some acidic character?
Not acidic enough to make that happen. Yeah. All hydrogens are measurably acidic at some level, but they're not acidic enough, because the base that would be produced by pulling those off would be an even stronger base than this. Yeah.
How are those Grignard products named? Is that important?
No, I'm not happy to name Grignards. Questions. All right. So super strong bases, got to keep it super dry. Other things. Okay. No, we're good to go. So we've got organolithium, we've got our Grignard, and now we've got Gillman reagent. So the Gillman reagent uses copper as the metal. So you're seeing a trend here. All these metals, when you can get a metal to form an organometallic complex to a carbon, will allow the carbon to hold most electrical density, giving it its partial negative character, which lets it behave like a hydride. The Gillman, because the copper is not, let's see, that's the best way to say this, is going to be less electronegative, and therefore less reactive. To be fair, every time I spell Grignard, I phonetically in my head call it the Grignard. So whoever, what's that spoof science fiction movie with Tim Allen where he plays the, it's like spoofing on Star Trek? Galaxy Quest, right? Remember when he's fighting the rock monster and all the little things are, what? Grignard. Every time I see that, I think it was like Grignard. Yeah, exactly. Excellent. This is
okay.
Like this isn't news to anybody. Okay, so a little less reactive, that allows it to react with a larger suite of compounds, which we'll get to in just a second. But let's review the reaction. because time is of the essence. So to prepare this, you're just going to use, let's see, 2 equivalents of some organolithium compound. So the first step would be to prepare the organolithium compound with the hexanes by taking your organohalide, put it in with the lithium, in hexanes, gentle reflux, organolithium compound. The reason we need 2 equivalents of the organolithium is because when you put it together with your copper iodide, we're going to get a complex where in THF, plus lithium iodide. This is the Gillman reagent, where you have a pair of these alkyl groups. So whatever this R group was, and here's just a methyl group, but a pair of them coupled to a single copper lithium complex, and then the second lithium complexes with the iodide, which was bound to the copper.
Will it only work with copper 1 and never copper 2?
Yeah, because we're just using the copper iodide, so it's copper 1.
I didn't know if there's like a separate one for the copper 2 or, okay, chillin'.
Not that, well, there may be, but it's not this particular reaction.
Yeah, chillin'.
So the cool thing about this is the R group for this can be either a primary alkyl group, it can be a methyl group, it can be a aryl group, which is that conjugated, that benzene ring that we skipped. But if you see it, that is a tool you can use. It can be vinyl. And the vinyl is where stage 2 and good. And it can be allylic as well, where this is 1 bond away. From the double bond. So it can be directly bound to the double bond, 1 bond away from the double bond, bound to a benzene ring, primary or methyl. The only 2 things that you don't see here in terms of halide substitutions are secondary and tertiary. So not secondary or tertiary alkyl halides for the Gillman. That's the limitation of it. So what's the reaction look like? Well, we typically, once we've prepped a Gillman reagent, you can now use this to form new carbon-carbon bonds by attacking any alkyl halide. So both the R group here for organolithium compound can be any of these. And if we are now going to take this and react this with some alkyl halide to form a new carbon-carbon bond, that R group can be any of these R groups. So now we have a lot of different things we can make. So let's look at how that goes. Okay. Okay, so if we wanted to do a reaction where we're joining new carbon-carbon bonds using Gillman, you would prepare the Gillman reagent by getting 2 equivalents of your ethyl lithium compound, reacting with the copper iodide in the appropriate conditions, make your Gillman reagent, combine it with this vinyl bromide, one of these equivalents will act like a carbanion functionally. If you want to think about mechanisms, come in, attack this, kick off the bromine. We'll just pretend this is what it's like, and your product will be that. So in terms of predicting products, super straightforward. It's stereospecific. Which is great, because whatever the stereochemistry is around these double bonds is retained. So there's no inversion. If there has specific stereochemistry, you retain the specific stereochemistry, which is what we see here. Likewise, if we have something a little bit more complicated, like, let's say, this benzene ring with an iodine, and we want to put a carbon-carbon double bond on it to extend our conjugation out here, we can make a Gillman CH2. You take these two, just pull one out if you're predicting. You think of it as a carbanion with your free lone pair. It's going to come in, attack here, kick off the iodine as a leaving group. And that would be your product. So you have a huge diversity of ways to join carbon-carbon compounds now, as long as you aren't using a secondary or tertiary carbon. This is not this is aerial, which is benzene rings, which will start next semester. The very first chapter we'll do will be benzene rings. You'll see the chemistry of this is not like double bonds because of all of the ability of these to be in resonance, which makes them behave differently than just a double bond.
Also, the fact that the entire thing is planar, right?
Mm-hmm. Well, and it's planar because of that conjugation. One other component to this is that why would you use a Gillman versus a Grignard? One good reason would be you can do Gillmans near carbonyls. So if you've got this ketone, and this is a carbonyl functionality, whether it's ketone or an aldehyde, got a carbonyl. A Grignard is such a good nucleophile that it can come in and attack the carbonyl. The Gillman is just soft enough where it will leave the carbonyl alone and will attack the bromine preferentially, or the carbon bound to the bromine preferentially. So you can actually use the Gillman to get around. You can make new carbon-carbon bonds on something that has a carbonyl without worrying about having some cross reaction. I guess there is one other limitation to this that we really need to lean on, and that is that if you have acidic functionalities on your compound you're trying to react with, if this was a carboxylic acid, right? This would be the case for an alcohol, or for a thiol, or for an an amino group. Anything with, but especially for this because of this quite acidic proton, this is also an excellent base and will react with this as well. So one of the big broad limitations of using organometallics is you can't run them on compounds that have protons that are acidic enough to be pulled off by them. The Gillman is a little less basic than the Grignard. The Grignard would almost exclusively react with this first as a base, even before being able to do a nucleophilic attack on the carbonyl or on the alkyl halide. So, in addition to being constrained by secondary and tertiary, you can't have acidic groups on your target compound. I'm going to hit stop on the video before we run out of memory.